Yeah.
Needs to be down a bit. Yeah. Oh yeah, that's better. Yeah.
Okay. Good morning, everybody, in the room and on Zoom. So we start this morning session, and we start with Ben Safdi about stars. You changed the title? No.
I think I was assigned the title, so I made it
It was
shorter.
a bit longer.
Yeah.
Okay. Go ahead.
Great. So thanks a lot for the invitation to speak here. This is my first time at GGI, and it's really nice. I think I've presented virtually in this room a few times, but never actually here in person. It's much nicer in person. So today I want to tell you about novel astrophysical probes of axions. There's a variety of different subtopics that I want to try to go through, but I hope that I don't get through all of it. I'm not planning to get through all of it, so I'm hoping that you all interrupt me with questions and we can start a conversation. And the reason I want to have a conversation is I'll try to motivate in the first part of this talk. I think that the parameter space that I'll be discussing today is very motivated and interesting, and there's a real chance that if we keep on probing it, we'll actually discover something. But I think we need new ideas. I think we need to have a qualitative change in our sensitivity. And so keep that in mind as I'm talking. Don't just try to understand what I'm telling you, but try to think about how to do it better. And I'd be really happy to chat with people during the rest of this workshop about new ideas. That's really what I'm hoping to get out of this talk today, is some conversations with you all about how to do these different probes better. So this is the parameter space that we'll be living in throughout this talk. So you've seen this before, the axion-photon coupling, the axion mass. And I'm going to be focusing on two different parts of this parameter space: the parameter space of low mass axion-like particles and the parameter space of high mass QCD axions. So the common thread here is relatively strongly coupled axions from our perspective, so decay constants on the order of 10 to the 10 or so GeV. So let me start by giving you some motivation for why we might want to be looking for axion-like particles, in particular at very low masses, pushing down to smaller couplings. So we all know the explanation of the strong CP problem with the QCD axion. Let me just kind of lay out my notation here. So A is my axion, FA is the decay constant below the QC confinement scale. QCD instantons generate potential for the axion. When it minimizes that potential, it dynamically solves the strong CP problem. In the process, it acquires a small mass, around 10 to the minus 5 eV, for a decay constant of about 10 to 12 GeV. And also, very importantly for this talk, and for most of the talks this week, the axion couples to electromagnetism through an operator that looks like A E dot B AFF tilde. And this is inversely proportional to FA, but there's some model dependence which can enter into the numerator. Also important for this talk, axions coupled to fermions. So this is a derivative interaction, g mu A, and then the axial current. It's conventional to define a dimensionless coupling constant. I want to sit on this point for a second because I'm going to use this notation throughout this talk. So this is dimensionless. The reason it's dimensionless is because when you do physical processes, you can think it's convenient to integrate by parts, and then you apply the equations of motion, and you bring down a fermion mass. And so we put the fermion mass there just because that's how it tends to show up in physical processes. And also importantly for this talk, this contribution should be there. It should be there because there can be UV contributions to this operator, but even if there aren't UV contributions to this operator, there are IR contributions to this operator coming from one loop processes, such as this one shown here, assuming the axion couples to W's and Z's. So the IR contribution is the UV one, which could be order one, and then these small loop suppressed contributions here, where CW and CB are the couplings to SU2 and to U1. So I want to distinguish between axion-like particles and the QCD axion, but these words mean different things to different people, so let me tell you what they mean to me. So let's imagine the scenario of the string axiverse. So what do we expect of the string axiverse? We expect some large number n of pseudoscalars, and I'll say more about this in the next few slides. Generically, they would couple to everything, but the one linear combination which couples to QCD will get a relatively large mass from QCD. Instantons become the QCD axion mass eigenstate. But assuming that all of these axion-like particles have small bare masses, they either n-1 remain ultralight, but by definition, they don't couple to QCD because that linear combination got a mass from QCD. So an axion-like particle for me couples to everything, but it does not couple to QCD. So it couples to electromagnetism, it couples to fermions, and potentially there's a small bare mass, but there's no coupling to QCD. So the axion, as we're familiar with, can arise as the pseudo-Goldstone boson of a U1 symmetry, the PQ symmetry, which undergoes spontaneous symmetry breaking. So here I'm writing that field, the complex scalar field phi, which obeys a U1, some accidental global U1 symmetry. You have spontaneous symmetry breaking. Below the scale of spontaneous symmetry breaking, the axion is the Goldstone mode, it's the phase. But this picture has some problems. All is not well here, and that is the PQ quality problem. So recall the PQ quality problem arises from this expectation that quantum gravity should break global symmetries, which means that we don't expect to have accidental, very high quality global symmetries, at least without doing extra model building gymnastics. So generically, I could write down any Planck suppress operator that I wanted. Maybe that's your expectation, that I could write down any Planck suppress operator that I want that respects gauge symmetries, but doesn't have to respect any of my global symmetries. And so if I allow myself to do that, I can write down operators like this, where lambda could have some phase. And then when I minimize the potential for the axion, this contribution, A plus theta bar, should be 0 to solve the strong CP problem, but you can see now it's not 0. And putting in a decay constant 10 to 12 GeV, I would need to tune the magnitude of this lambda parameter to be less than 10 to the minus 54 to maintain the axion as the solution to the strong CP problem. So this is the dirty side of the axion, and it's a problem that we just have to face. So there are many different ways of facing this problem. The one that I want to highlight for the moment, because it's going to serve as some motivation for what I want to talk about, is to go to the one theory of quantum gravity that we do have, which is string theory, and ask how is this problem solved in the context of string theory. In the context of string theory, this is solved by having extra dimensions and having the axions arise from the 0 modes of these gauge fields compactified on extra dimensions. So let's look in a little bit of detail about how this actually works, because I want to get out at the end some numerical quantities which will motivate the parameter space we'll be probing. So let's just take an example first. So let me consider a 5D scenario. So I have 5 dimensions. I want to compactify that 5th direction onto some circle of radius r. So phi here is an angle, goes from 0 to 2 pi. A5 is going to be the 5th component of the gauge field. So the axion, the dimensionless axion field theta, is defined by the gauge invariant Wilson loop as the 0 mode integrated along that compact 5th direction. And then the decay constant Fa, you can figure this out just by starting with the 5D action for the 5D gauge field, and then doing the dimensional reduction and getting the canonically normalized term for the axion. You then infer what the decay constant has to be, and it's 1 over 2 pi r times that 4D gauge coupling, and the 4D gauge coupling is related to the 5D gauge coupling in the usual way. So let's now go and put in some numbers. So we might expect that that 4D gauge coupling approaches that at high scales of supersymmetric grand unification. Let's take that for now. So let's imagine that G4 squared over 4 pi is 1 over 25. Let's imagine that the size of that compact extra dimensions on the order of the string scale, so something like 1 over 10 to the 17 GeV. There's some pi's, there's that G4, so you put in the numbers and you get a decay constant of about 10 to the 16 GeV. And this is what was originally thought to be the generic prediction in the context of string theory. So if you look at this canonical paper by Whitten, you'll find this number all over the place, Fa of 10 to the 16 GeV. And indeed, that's the motivation for experiments like Abracadabra and DM radio, which is a abracadabras experiment that my collaborators and I proposed a few years back, and it's now turned into a real experiment. You can see our upper limits up here, and it's being followed up by the GM radio program, which I believe we'll hear a little bit about this week. And we have this kind of ambitious set of 3 experiments that are being planned and built, and we can have discussions related to those, which are aiming for, as you can see by the name of this experiment, GM radio gut, are aiming for this FA of 10 to the 16 GeV corresponding to a mass of around a nano eV QCD axion. But one thing that I find very interesting is that this expectation of, in string theory, decay constants on the order of 10 to the 16 GeV has changed a little bit in recent years. And so let me tell you about some recent work. This is not my work, this is work, string theory work, which I find very interesting. So first, let's just understand at one more level of complexity how axions arise in the context of string theory. So let me take type 2B string theory as an example. So you have this 4-form field, which is morally just the more complicated version of that 5-dimensional gauge field I just showed you. And you can compactify it. Well, we have to compactify these extra 6 dimensions. And so axions, theta I, are 0 modes. So they're given by integrals along 4 cycles of this 4-form field. And the number of axions is given by the number of 4 cycles. So this number H11. And you can follow the same procedure for figuring out the decay constant by canonically normalizing the axiom. You'll see that the decay constant scales like the Planck scale and then inversely proportional to the dimensionless volume of these 4 cycles. But one thing which is very interesting, going to some recent string theory work by many different groups, but I'm just showing one here by McAllister and company, is that as you look at manifolds with increasingly large numbers of axions, the volume of the largest cycles seems to increase like a power law with the number of axions that you have. So you can see over here going up to say 100 axions, the volume of the largest cycle has increased by a factor of 10 to the 6. And that volume shows up here in the denominator, and that drives these decay constants to be lower in these theories with large numbers of axions. So you generically thought that all the decay constants would be 10 to the 16 GeV, but you can see here you end up with some which are actually much smaller. So here's another paper by James Halverson and collaborators, another set of string theory compactifications where they find the same thing. So here it's being plotted as the axion photon coupling. You can see as they go to increasingly large numbers of axions that their axion photon coupling distributions move up and up and up. And so that tells us, as theorists who are more connected with data, that we should be moving down and down and down. And there's actually a chance that we're going to intersect where these models live. Not by me, but I've asked for some intuition from Liam McAllister, and he wasn't able to give me any intuition either. So I don't know. Maybe someone has some intuition, but I yeah, so the intuition I've heard is just that you accidentally end up with some large cycles. You know, that most of these directions are most of the cycles are kind of string length, but some of them, because these geometries are becoming complicated, end up accidentally large. But I don't, there's probably some geometric explanation there that someone could give you, but that person's not me. Yeah, but it's an interesting question. And it's interesting that different groups find it. The impression I have is that these manifolds that McAllister and company are using and the manifolds that Halverson and company are using are very different. They're constructed in different ways, but they find the same growth. So the motivation for us then, or at least for me here, is to push down. We heard a lot yesterday about some very interesting probes of low mass axion-like particles and high mass QCD axions. And I think this just adds farther motivation. And it really adds motivation to even just incrementally increasing our sensitivity, because there's a real chance of discovery here. So I'm going to be talking about a completely different set of probes to the ones that we heard yesterday, essentially because, well, we don't want to repeat the same thing, but also because I want to tell you about the stuff which I've been involved in, because that's the science that I can tell you about with any authority. So I'm now going to switch gears completely, and I'm going to go through a sequence of projects that I've worked on recently in this philosophy of pushing down the sensitivity to low mass axion-like particles. So the first probe that I want to discuss is using magnetic white dwarf polarization. And so that's this curve shown here, and I want to tell you what we did to get that curve and what we can do in the future to increase the sensitivity here. So first, this is a paper that came out last year with Chris Desert, who was here, I believe, a few weeks ago, and David Dunsky, who was also here a few weeks ago. So Chris was my grad student, and David was also a grad student at Berkeley. They're both now postdocs at NYU and CCA. So the idea here is that we're going to be looking at unpolarized light, which is emitted from the surface of a white dwarf, just thermally. And we're going to be looking at white dwarfs with large magnetic fields. These are called magnetic white dwarfs. Though that light will travel through this region of magnetic field, and the light which is polarized parallel to the magnetic field can convert to axions. Those axions are unobserved, and this induces a linear polarization from us, the observer. So we're going to be looking for linear polarizations, and if we don't see a linear polarization, we can set an upper limit on the strength of the axion-photon coupling. Yeah.
I ask a different.
Yeah.
One expects also circular polarization.
Yeah, it's a good question. So it turns out if you work out the mixing equations, axions do induce a circular polarization, but it turns out to be actually lower order. In appropriate perturbation series, it's lower order process. So that's the one kind of hit against it. The other point, which I'll return to later, is that there are astrophysical processes in the white dwarf atmospheres which create circular polarization. They also create linear polarization, but at lower order. So the linear polarization seems to be the higher signal to noise process to look at. Okay, so this is the same picture, just shown differently. Unpolarized light, magnetic field, observer. And we're going to be using this interaction AE dot B. So the point here is that if B points this way, only the E fields parallel to the magnetic field can convert to axions. And that's why this is a polarization dependent process. So as a side note, it turns out, you might be thinking in the back of your mind already, maybe I can do this with neutron stars. They have even stronger magnetic fields. It turns out magnetic white dwarfs are the optimal targets, at least for stars. And the reason is that neutron star B fields are actually too large. And the Euler-Heisenberg term, which I'll mention later, suppresses the conversion probability for neutron stars. So the way that you do this in practice is you write down mixing equations for the axion and the photon. This is the vector potential polarized along that magnetic field direction. You then make some approximations to reduce the second order differential equations to a set of first order differential equations, a WKB approximation. The important part of this differential equation is this mixing matrix. You can think of this as a Schrodinger type equation. And there's some mixing matrix. So the diagonal terms are essentially mass terms for the axion. That's the axion mass, which we're going to ignore for now. And then there's this Euler-Heisenberg term, which turns out to not be important at the frequencies that I care about. This is a nonlinear correction to Maxwell's equations coming from integrating out the electron. But I'm going to return to this term later. So let me not say any more about this for now, and we'll come back to this term later. So for the moment, you could ignore both of these terms in the diagonal. Then we just have this off-diagonal term, delta B, which scales like our axion-photon coupling. That's what gives us our mixing, and the magnetic field that we have to work with. So the polarization fraction, the linear polarization fraction, you should work this out with some formalism, but you can kind of guess the answer by looking at 1 minus the photon-photon conversion probability. So that's the survival probability for photons. So 1 minus the photon-photon survival probability is a pretty good approximation for the linear polarization. And if you compute this, it's essentially g squared b squared times the distance over which you're traversing squared. So let's just substitute in those numbers. Let me put a g gamma gamma of 10 to the minus 12 inverse GeV, a magnetic field of about 1,000 megagauss. I'll motivate that number on the next slide. And then typical size of magnetic white dwarf around 0.01 solar radii. And you put in those numbers, and you end up with about a 1% polarization fraction. And that's about at the level that we can currently probe. So this suggests to you that we should be able to probe Ga gamma gamma on the order of 10 to the minus 12 inverse GeV. Of course, you need to solve this actual differential equation, not just this approximation, which I'm showing here, but that's what we expect. So in practice, we solve this numerically. We include this Euler-Heisenberg term. We also include non-radial trajectories which come from the top of the magnetic dwarf, from the sides. But this is a pretty good approximation to what we find at the end of the day. So let me now just take a bit of an aside and go through some stellar physics to motivate this 1,000 megagals. So if you knew some aspects of non-compact stars, you could have immediately guessed that we would have stars with magnetic fields on the order of 1,000 megagals. So how would you have done that? You would use this general expectation that stellar evolution approximately conserves magnetic flux. So let's take normal stars, and let's look at the normal star with the largest observed magnetic fields. That's the star HD 215441, and it has a magnetic field of about 3 times 10 to the 4 Gauss, but it has a radius on the order of the radius of our sun. It's a normal star. And let's suppose that the star becomes a white dwarf. So its radius is going to drop to 0.01 solar radii. Then the magnetic flux to be conserved, the dipole strength should increase like the ratio of those radii squared. And so you put in the numbers and you end up with a number right about 1,000 megagauss, 10 to the 9 Gauss. And that's actually what we observe when we look at the most strongly magnetized magnetic white dwarfs. Of course, there are also stars like our sun, which have much smaller magnetic fields. So it's not that we expect every white dwarf to have a magnetic field of 10 to the 9 Gauss. Some of them will essentially have no magnetic field or very small magnetic fields, but some of them will have large magnetic fields. And those are what are called magnetic white dwarfs, not just a white dwarf. Yeah. I can also repeat the question if you.
Yeah, sorry. When the star becomes white dwarf, it should also the outer layers go away. So cannot they carry away some magnetic flux?
Yeah, so good. That's a good question. Yeah, but I said approximately conserves magnetic flux. Yeah. But let me tell you how we actually measure the magnetic field. So we don't just rely on several evolution models. I just wanted to motivate for you why these scales aren't surprising. But here's how we actually measure magnetic fields. So we measure the magnetic fields using the Zeeman shift. So the white dwarfs are surrounded by thin atmospheres. Those thin atmospheres have hydrogen, and in those hydrogen atoms can undergo bound-bound transitions, and these absorb light. So what you're seeing here at the bottom, this is SDSS data, and you can see that there's an absorption dip, and that absorption dip corresponds to this transition between these two states in hydrogen. So, and that's for this specific magnetic white dwarf, which we're looking at here, which turns out to be a magnetic white dwarf where we have linear polarization data. So what you're seeing in this top panel is as we change the magnetic field, so as we go up the y-axis, what is the absorption wavelength of this transition? And you can see as you go up and up and up in magnetic field, the transition wavelength changes and it goes up and up and up also. So if you have a dipole field, which is a good approximation to the magnetic field of a white dwarf, then you're going to see different magnetic field strengths on the surface. So it's not just one magnetic field, it's a distribution which is set by the strength and the inclination of that dipole with respect to us. So what you're seeing here are the absorption templates for 2 different dipole magnetic fields, where for these dipole magnetic fields, I've chosen the inclination that gives the best fit to the data. So for the 400 megagauss magnetic field, you can see that looks nothing. It's not going to look anything like the data. But the 700 megagauss field is going to be able to reproduce this dip. And then at the bottom, you're seeing our absorbed thermal model. And that prefers a magnetic field for this particular white dwarf about 760 megagauss. Of course, we don't just do one transition. We have many transitions available to us, and we fit all of them. We fit the model to all of them simultaneously to determine these magnetic fields and the inclination angles with pretty good precision. So the magnetic fields of these systems are pretty robustly measured because we have these hydrogen absorption lines to go off of. So what you're seeing here is a linear polarization fraction on the y-axis. On the left panel is a function of the inclination angle with respect to us. So Notice this goes to 0. The linear polarization fraction from axions goes to 0 when there's no inclination angle with respect to us. This had to be the way by symmetry. Imagine if the dipole is pointing towards us, where would the linearization point? There's no preferred direction, so it has to go to 0 by symmetry. So from this SES data, we can constrain the inclination angle with respect to us to be within this orange band. And this is for a G gamma gamma of 10 to the minus 12 inverse GeV. And we fix the inclination angle to be the most conservative value at 1 sigma, which is that orange band there. Similarly, we can constrain the magnetic field dipole strength to be within this orange band, and we fix it to be at its most conservative value here in the analysis. So then there's the data, and this is where this nice story gets very messy, because white dwarfs don't produce linear polarization, astrophysical linear polarization. And one thing which particle physicists love to do is to look for something where there's nothing, but astrophysicists typically don't like to do this because they actually want to measure something. So that means that there just isn't that much archival data to use of linear polarization towards magnetic white dwarfs. So we were able to find a few data sets. This is one of them. This is from this Russian telescope, this 6-meter telescope here. It was essentially the only relevant archival data that was available to us. But the data was messy. The documentation was even messier. So we kind of had to hack together an analysis. And so let me just tell you what we assumed. You can see the linear polarization fraction is a function of wavelength. It looks like they detect the linear polarization fraction, but this is actually just a systematic offset. So there's some constant systematic offset that's correlated across all wavelengths. We don't know what it is, so we treat this as a nuisance parameter that we essentially profile over. In addition, there could be some astrophysical contribution to the linear polarization. That comes from the fact that in the presence of a magnetic field, you have splittings from the Zeeman shift of the bound-bound, the bound-free, and the free-free transitions. And these then depend on since they're split by the Zeeman shift, they depend on the polarization of the light. So some polarizations will be preferentially absorbed by hydrogen, and that can induce at some level linear polarization. We can predict the spectral shape of this, but we can't predict the magnitude because that depends on the depth of the atmosphere. But we expect it to be actually much smaller than what's shown here. So we profile over over a functional form like what's shown here, but we find no evidence for that in our messy data set. And then at 95% confidence, our best guess for the upper limit for an astrophysical contribution, for an axion contribution is what's shown up here at 1.2%. So our upper limit at 95% comes from not overtaking what's shown up here. And that is essentially coming from our guess of the systematic uncertainty associated with this instrument, but it's not documented, so it's a guess. And that translates to the limit that you see here. So what you're seeing here in red is our fiducial 95% upper limit on G gamma gamma, which I think is pretty robust because we can measure these magnetic fields very well. You can see in orange, that's the effect of the astrophysical uncertainties. So if we were able to improve knowledge of the magnetic field and the inclination angle, we could perhaps collapse this to somewhere in there, but you can see it's relatively minor. So one interpretation is in the context of these gamma ray transparency anomalies, which we heard about yesterday. And so I'm not going to go through the explanation of these anomalies because, again, it was explained yesterday. But one immediate result of this work is to constrain, or I guess rule out, the axion as an interpretation of these anomalies. Yeah.
Hi. Just a general question on the magnetized white dwarfs. So are they a population that separate from white dwarf, or are they like a fat tail in the distribution of magnetic fields?
They're not separate. They're just white dwarfs, which happen to have larger magnetic fields. So they came from stars, which happen to have larger magnetic fields.
So you can think of a distribution of.
There's a distribution, sure.
Fields,
yeah, that's right. So magnetic, I don't know what the precise cutoff is on magnetic field for something to be called a magnetic white dwarf, but yeah. Yeah, good. So the bound turns up. So the question was, why does the bound turn up? And the bound turns up because at this point, you can't ignore that mass term in the equations of motion anymore. So at this point, the axion and the photon will decohere during that transition. You'll no longer have resonant conversion anymore. Yeah. Other questions? So what are we doing now? We're trying to get our own data so that we can actually understand the data side of this better. So we're trying to collect data at the moment from this UC Lick, the Shane telescope at the UC Lick Observatory. So here's where I live in Berkeley, California, right next to San Francisco, and a quick 45-minute to 3-hour drive, depending on traffic, will take you to this Lick Observatory down here in this telescope. And so Chris and Cristiano, who's a postdoc at Berkeley, we've teamed up with Alex Filippenko, who's an astronomer who actually can take this data to try to collect some dedicated linear polarization data. And if you've been looking at the news, it's been a very wet winter in California, which has actually been a problem for us because we haven't been able to take the data yet. And now it's foggy. But starting in the fall, we'll start to be able to collect some of this data. We've actually already collected a preliminary amount of data. And assuming that we only see the null hypothesis, we're going to be observing 3 different magnetic white dwarfs, which are within our field of view. And these are the 95% upper limits that we should be able to produce by the end of this year. So hopefully at the end of 2023, you'll see upper limits like what's shown here appearing. And so this corresponds to about a 0.1% systematic uncertainty in this instrument on the linear polarization. I think the best that you could probably ever do is down somewhere around here, which would correspond to 0.01% systematic uncertainty and no observed astrophysical linear polarization. But that's already pretty futuristic, I think. That kind of tells you where this sort of probe is expected to bottom out. We probably won't be able to push much below 10⁻⁻12 inverse GeV. So it's a relevant probe, but this is not going to be the one that brings us below 10⁻13 inverse GeV. So I want to switch gears now. I want to keep on talking about magnetic white dwarfs, but
It is customary when you talk about everybody talks about axion to give limits. But if there is an axion, so what would you see? What is the confidence that you could claim a discovery?
Yes, that's a great question. Obviously, yes, we're in this business not to set limits. We're in this business to discover something, but until that day, we're going to set limits. But it's interesting to ask how we would gain confidence in a signal here. And that's actually pretty hard, because if you see a signal, how do you differentiate it from an astrophysical? First, how do you make sure it's not a systematic in your instrument? Okay, we have instruments that we understand in this case. So that I'm not too worried about. But how do you make sure that you're not seeing some astrophysical contribution to linear polarization? And that's harder. So I showed you here what our template is for the astrophysical emission. You can see it has a lot of features. These features come from different bound-free transitions. So the fact that hydrogen is inducing the linear polarization, and hydrogen has absorption lines. So we expect to see features, whereas the axion contribution is shown in red, and it's just flat. That's one possible handle, but I don't know if we're not going to claim a discovery off of that. I think, honestly, this is a bit of a hard discovery channel. So we might see some hint here, but there are cleaner probes that you would want to follow up with. Yeah.
So if I understand correctly, then during your data analysis, you basically marginalize over some of your nuisance parameters over other data sets, and then to obtain the limits, you use sort of these, probably conservative but still fixed parameters. Is that right?
That's right. Yeah.
So, sometimes it could be that if you did a simultaneous fit of everything at the same time, that this would still, shift around things, because you might, systematically, by fixing the parameters, influence the fit. Did you did you check that that's not happening, or did you do, for example, some, I don't know, for example, some Bayesian analysis as a cross check of this to?
Yeah, so there are no kind of magic cancellations that show up here. So yeah, it's not like the axion can become kind of degenerate with something else and give you some flat direction in the likelihood. So different ways of doing this analysis can shift around your upper limit, but they will shift it around on the order of this, or actually small. This is kind of the maximum amount that you would expect to see something shift around.
I mean,
So
guess,
yeah, if you do, we did experiment around with different sorts of analyses, and yeah, you'll get a different upper limit, but it's morally going to look similar to this
I
one.
mean, I guess what always helps you is that it's g to the 4, and so on the plot it won't, change things around. But since the error in the inclination angle, for example, is quite large. I mean, if you fix that to some value, and then I don't know.
Yeah, and if it was if everything was just statistical uncertainties, then we would do what you're saying. But because there are there are systematic uncertainties here that we're just guessing, then it makes just doing one kind of unified likelihood treatment a little bit overkill, because we're just guessing priors on nuisance parameters.
Yeah.
So in the world in which we understand all of this better, then yeah, some kind of more some just full likelihood treatment is probably more justified, but we're not at that stage yet.
Yeah.
At this point, this limit is a little bit of a hack because we're just literally guessing how this instrument works.
Yeah, fair enough. Thanks.
Sorry.
Oh, question in the back. Oh. Does what domination? Age determination. Does age determination for the white dwarf matter? Not what I want to show you here. Not what I'm showing you here, because it's just a black body. It's a black body. It's a candle that happens to be sitting next to a magnetic field. We don't care how old that candle is. It's just a candle. That's all we're using it as. Yeah.
Hi, sorry. So I'm still thinking about if you, made an exciting discovery, how you would sort of look at the background. So you mentioned you have 3 magnetic white dwarfs in your field of view. Is that just a Lick thing, or how many?
That's just a Lick thing, and it's a Lick thing, and just the amount of time that we got to observe. We could look at more. You could look at more if you were somewhere else. We could look at more if we had more time.
So is there something, say if you saw a hint of something and this was sort of motivating to look more, like how many of these things could you access if you looked at different telescopes there? And is there something to sort of looking at magnetic white dwarfs in different fields of view to sort of, I don't know, average over astrophysical contributions, because presumably the axion signal should persist?
Yeah, that's a good question. And it's not something that I've thought about in a lot of detail, but yes, I mean, there are many. I don't know the number of magnetic white dwarf targets that we have available to us that would be competitive. You want ones which have magnetic fields on the order of kind of 700 megagauss. But there are a lot. There's a lot. And yeah, they should all have different signal strengths depending on precisely what their magnetic fields are, their inclination angles. Another thing which I didn't, there are actually a few other handles. Some of these are rotating fast enough that you can actually see the rotation. None of these are. None of these are, but some of them are. And there you actually would see the linear polarization change as a function of time on that magnetic white dwarf day in a very predictable way. And so there are a few other handles that you have that you could go off of. Yeah.
Actually, speaking of the rotation, do you know if there is any highly magnetic white dwarf that at the same time where you can estimate this period decrease? Something.
There are. I think there's actually limits, if I'm remembering correctly, on axions coming from something related to period decrease of a particular magnetic white dwarf.
Okay.
Yeah.
So one of them is okay.
We can discuss that afterwards. I'd have to look up the paper.
Yeah.
Okay, so now let me just briefly change gears. We're going to stick with talking about magnetic white dwarfs, where we're going to look, and we're going to keep on talking about axion photon conversion, but now I want those axions produced in the core of the magnetic white dwarf through processes like this, where degenerate electrons scatter off of ions, they brim off an axion. And now these axions are converting to photons. So remember before, photons were converting to axions, we weren't seeing the axions. Now axions, which we were never going to see, are converting into photons, and suddenly we're going to see them. And we're going to be looking for these with X-ray telescopes because these are going to be X-ray energy axions. So I should say this is a sequence of papers that I've been kind of developing over the past few years with Chris and also with Andrew Long, who used to be my postdoc and is now faculty at Rice. So the idea here is that the flux coming off of a white dwarf is cool. This is kind of that EV level thermal emission that we expect to see, which I've been discussing. But the core is hot. This is like a thermos or something with hot coffee inside. And you just can't tell that there's hot coffee inside because you just see the cool surface. But axions could give us a way of seeing that hot coffee inside because the axions are able to escape the core. And then what we're looking for would be this X-ray emission up here at high energies coming from axions. So in our recent paper, we looked at this particular magnetic white dwarf, RAJ0317. This is a white dwarf which is relatively close by. That matters for this. It has a pretty large magnetic field, about 500 megagauss. Again, we measure that with Zeeman splitting. And it has a pretty high core temperature of about 1 keV. That sets the scale for the energies of the axions we're going to be looking for. And again, astrophysicists don't like looking for nothing. So there were no relevant astrophysical data sets, so we had to go out and collect it ourselves. And we're awarded time to look at this particular white dwarf with Chandra. So first, we need to calculate the signal. So the axion luminosity, which we produced in the core of this magnetic white dwarf, is about 10 to the minus 4 solar luminosities for GAEE of about 10 to the minus 13. Remember, GAEE is dimensionless because it has the electron mass in the numerator. And you can understand this TC to the fourth in the following way. So let's count. One factor of TC is because we're calculating a luminosity. So we need to multiply by the energy of the outgoing axions. Okay, so we have one factor of TC. The electrons are degenerate, which means they need to scatter into a free state. But most of the electrons, since they're degenerate, can't scatter into free states. They need to be living within a temperature of that Fermi shell in order to be able to scatter up into a free state. And that brings in a Fermi degeneracy factor of TC over PF squared. So now we have 3 of the 4 factors of TC, and the 4th factor of TC comes from a spin flip, which is associated with that vertex. That's the last factor of TC. The last complication here, when you calculate the emissivity, is that the ions that you're scattering off of, shown here as N, form some sort of lattice within that magnetic white dwarf. And so you need to account for the interaction, for the scattering essentially within that lattice. But this is something which astrophysicists and nuclear physicists have worked out. And so we can use these ionic correlation factors to just kind of bootstrap into our analysis. The other complication here is that we're now doing axion photon conversion at much higher frequencies. We're now at keV as opposed to EV. And that means this Euler-Heisenberg term, which shows up in this mixing matrix, becomes important. So the Euler-Heisenberg term comes when you integrate out the electron in the context of QED. And it modifies the dispersion relation of the photon. It gives it an effective mass depending on the magnetic field and the frequency. So at larger magnetic fields is more important, but at larger frequencies is more important. And this suppresses the conversion probability. So this axion to photon conversion probability is shown here for a G gamma gamma of 10 to the minus 12 inverse GeV. All of the other parameters here are the same as what I showed you before for the linear polarization, except the frequency. But before, this number was 10 to the minus 2, and now it's 10 to the minus 5. And it's 10 to the minus 5 because of that Euler-Heisenberg term and the fact that when we go to higher frequencies, that suppresses the conversion probability of axions into photons and photons into axions. That's just a fact of life we have to deal with. So we collected data at the very end of 2020 from a dedicated observation with Chandra, 40 kiloseconds of data. We analyzed that data from 1 to 9 keV. We were super excited when we got this data set. I remember it was right around Christmas. It was like a Christmas present. This data set came and we opened it up and it was the most disappointing thing ever because we saw absolutely nothing. We weren't even sure we were looking at the right part of the image because how do you know if you're looking at the right part of the image if there's nothing to tell you what you're supposed to be seeing? So this is our source here, and this is how the signal would appear using the PSF of Chandra. And you can see there are actually absolutely no photon counts which hit. The photon counts which you do see just show up in random spots. So it's background-free analysis, but no signal. So that tells us that we can go ahead and set upper limits, and this is an illustration of what a signal would appear like as a function of energy for a decay constant, kind of a generic decay constant about a few times 10 to the 9 GeV. So our signal is a product of the axion photon and the axion electron coupling. So the parameter space that we can constrain is a kind of diagonal in that plane. So you can see up here, we're excluding things to the right of this line. So we heard yesterday about these cooling hints, and we can constrain these cooling hints not for a QCD axion, but for an axion-like particle. We can also convert this constraint into a constraint on G gamma gamma alone if we make some assumption about the relationship between the axion electron coupling and the axion photon coupling. And there's kind of two justified choices you can make. On the one hand, you could assume that you have a tree level axion electron coupling. Why not? That could be the case. And then our upper limit on G gamma gamma would be something like what's shown here. So that's assuming a tree level coupling to electrons. On the other hand, you could not couple to electrons at all in the UV, but remember that you're still going to get a contribution in the IR. But that contribution in the IR comes from how strongly you talk to W's and to SU2 and to U1. So let's assume the more conservative choice, which is you don't talk to SU2 at all, you only talk to U1. And then our upper limit becomes that shown up here. So depending on where you are, you have a different sort of upper limit on G gamma gamma alone. So what are we doing now? So coming in 2023, we have new Chandra observations that were awarded to us, a total of 80 kiloseconds of time. And we're following up on two brand new magnetic white dwarfs. Our most optimistic one is this white dwarf 1859. And this turns out to be much hotter, or we estimate it's much hotter in the core than the previous one that we looked at, such that our sensitivity should actually jump by almost a factor of 5. So this is going to be super exciting. We don't have that data yet, but that data should be coming soon, and will be a pretty big jump in sensitivity. And again, this, to answer the question from before, here it's easier to say how would we see a signal, because we're really just looking at an image. We don't expect to see anything, and then if we see something, that doesn't mean we've discovered axions, but I think it would be easier in this case. Yeah, so it's a good question. There are two different features which are affecting the shape of this limit at high mass. One is the mass itself, but the mass has two things to compete with. The mass has to compete with the off-diagonal terms, that G gamma gamma B term, but it also has to compete with the Euler-Heisenberg term, which was relevant. So there's two bumps depending on when the mass term passes the Euler-Heisenberg term. That's kind of the first bump. And the second bump is when the mass term then surpasses the G gamma gamma B term. There's 3 dimensional parameters, and you're increasing one of them, and you have 2 thresholds to pass. Before, you only had 1 threshold to pass. So we can apply this same philosophy towards neutron stars. And so let me tell you briefly, just in a slide or two, about how this works. So this is coming from a paper that I wrote with Chris again, and then Malta Bushman, who was a postdoc of mine at the time, and Raymond, who was a postdoc of mine at the time. Malta is starting a postdoc in Amsterdam next year, so we'll be in Europe. And Raymond just got a faculty position in Indiana. So the idea here is exactly the same. We're looking for axions going into photons, but now those axions are being produced in the cores of neutron stars from scattering off of nucleons. But otherwise, the search is exactly the same. So we got a little bit lucky when it came to this neutron star search, because there was actually a lot of archival data that we could use already. So in particular, there are these 7 neutron stars called the Magnificent 7, which are soft X-ray sources. So they have surface temperatures about 100 eV. That's significantly hotter than the surface temperature of a white dwarf. And it means that the thermal emission from the surface actually gets up into soft X-rays. And these are actually such good black bodies from the surface that they are calibration sources for both XMM Newton and Chandra. So both Exum, Newton, and Chandra stare at these things like every month to calibrate their instruments. But as far as we are aware, we are the first people to ever open those data sets above 1 keV. They just look at it below 1 keV because they're looking at the thermal emission, but they were collecting all this high energy data, which was super useful for us. So these have large surface magnetic fields, about 10 to the 13 Gauss. Those are measured by spin down, and they're all pretty old and isolated. And when we opened the data, we actually found something pretty interesting. So this is one of these magnetic white dwarfs, 1856. We saw that thermal emission coming down from the surface. That was to be expected. But then we saw excess hard X-ray emission coming from the surface of this neutron star. And that got us excited because that's exactly what we would expect to see if we had an axion-induced signal. And it wasn't just this particular neutron star. We saw excesses in many of these magnificent seven. So in green and gold, you're seeing our intensities that we measured from these neutron stars at 1 and 2 sigma. And then the black and gray are the model predictions for the best fit couplings. You can see that the model predictions are generally following the data. So that also got us very excited. And if you can interpret this data in the context of the axion model, the best fit parameter space is slightly below current constraints, which got us even more excited. But to tell you the truth, I'm now slightly less excited about this. And the reason is that given these white dwarf constraints that we've gotten both from polarization, but more importantly, the ones from X-rays, if this is actually due to axions, it would need to be an electrophobic axion. It would need to couple to quarks more strongly than it does to electrons. Maybe you're fine with that, but if you want the most generic thing you're going to pull out of a box, it's probably not this. So I think that the jury is still out on what exactly this is, but my own prior on axions has gone down a little bit. It is. That is what happens in the KSVC axion.
What you should expect.
Maybe, yeah. I just, you know, when I opened that white dwarf data set and didn't see anything, my prior just sunk. But maybe your prior should not sink. Yeah, it is what you expect in the context of that model. That's a fair point.
Okay.
Yeah.
So then,
Maybe I'm overselling the downside of this too much. Yeah. I mean, we should figure this out on its own, independent of anything else, and that's what we're trying to do now. So we obtained observation time this year with New Star, who are interested in us figuring out what's going on. So I should say, by the way, since our papers on this, this excess has been confirmed by a few different groups. This excess exists in the Exum, Newton, and Chandra data. That is now established. What's not established is what is this? And axions aren't the only explanation. There's some other kind of wacky astrophysical explanations which have emerged also in the past year or two. But one way to differentiate these explanations is to go to higher energies, because we expect a thermal distribution which should start to turn over, whereas for astrophysics you might expect something that's not thermal at all, in which case it would keep on rising with energy. And so one way to differentiate this is to look at high energies with and you need a telescope that can look up there. And so the one that we can use is New Star. And so New Star has sensitivity up to higher energies. And we're collecting data this year with New Star, and that should shed some light on this. Yeah. Could what, sorry?
EAXO.
Yes, or EAXO or ALPS 2. Yeah, so it would need to be sitting right below current constraints. So yeah.
Go back one slide.
But it's hard to do a direct translation because this involves the axion-nucleon coupling. So, and another thing I should say, there's a lot of uncertainties here on the nuclear side of the nuclear equation of state plays a role, superfluidity plays a role. And so this best fit parameter space can move up and down a little bit. But just to translate to EAXO or to ALPS 2, you have to make some translation between the axion-nucleon coupling and the axion-photon coupling. So potentially one of them could see it, but you would have to lucky in some sense.
Do you see excess for all stars with this temperature, or some stars show the excess, some stars don't?
We see excess at mild significance for 4 of the 7 magnificent 7. So you can see here that some, like this J1605 is consistent with 0 at 1 sigma.
So some stars do not show any excess.
Yes.
How you can explain that?
Well, you can see the model prediction shows that too. And the reason is some of these are closer, some of them are farther away. Some of them have stronger magnetic fields, some of them have weaker magnetic fields. Some of them are older and cooler, some of them are younger and hotter. So that's all wrapped up in this model prediction. That's what we expect, a diversity of signals, just because we're looking at an ensemble of neutron stars with different properties.
Do you see similar excesses in different neutron stars?
These are the only 7 that we have available to us. So E Rosita might give us more isolated neutron stars, but at the moment, there's only 7 nearby isolated neutron stars that we can point at. Yeah.
Can you use the spin of the neutron star as a tool?
The spin of the neutron star, so from spin down, that's how the magnetic fields are estimated.
No, I meant the modulation,
Mm.
magnetic field by the spin.
Yeah, we've thought about this, good, but our statistics are really low. So yes, there should be, well, first, these are old neutron stars, they're pretty aligned. I don't actually think even in the thermal emission, you see, I don't think from any, you hardly see anything. It's really hard to see the actual spin of these. You do see the spin because that's how the spin down is measured, but it's really small because they're almost aligned. These are very old. And then we have very few statistics, like low numbers of counts at high energies. So to collect the statistics to actually be able to see something modulating at high energies is not really feasible with any of the instruments present. None of these are pulsars, actually. But pulsars, we could look at pulsars, but they turned out to be much worse for this. They're mostly farther away, and they might have, and they also have non-thermal background. So the thing with pulsars is they create hard X-rays non-thermally, and that would just swamp this signal. So we have to look at things which are below the pulsar depth line.
I bet you don't measure the polarization.
We don't measure polarization because the instruments we're using don't measure polarization.
But you could ask them to.
We could not ask Newton and Chandra because they aren't sensitive to polarization, but there are other telescopes which are already launched or launching, which will look at these in polarization. Yeah, and that's another interesting handle for sure, because this should be polarized. Yeah.
And I see there is some dependency on the axion mass in the fit.
Yes, no dependence.
There's no dependence.
There's no dependence, yeah. Are you asking why?
It just the intensity of the signal drops for higher masses because again, the signal doesn't go to higher masses.
Yeah, good. So what happens when you go, so the mass only affects the conversion probability here. And when you're at low masses, you don't notice there's a mass. That's why it's flat. When you go to high masses, it affects the conversion probability, but it starts affecting it for the low frequency photons first. So what that does is it makes the spectrum harder. It makes it have more power at high energies relative to low energies. It steepens the profile. And that makes it more inconsistent with the data, which is why, like, this could have converged higher had it been a more high energy excess than it was. If that makes sense.
How are you accounting for the angular parameters in the analysis?
Of the magnetic field?
Well, yeah, so the orientation of the star relative to us.
Yeah.
This alignment angle between the field, and then in principle, there's also the angle associated to the intersection of the trajectory with the magnetic field line.
That's right. Yeah, good. Let me try to remember the answer to all of these. So for the production side, it doesn't matter. It only matters for the conversion. Just a thing to say before answering your question is, since we're in this Euler-Heisenberg regime, see if I can find the plot. We're actually less sensitive to the magnetic field than you would naively think. So the conversion probability scales like the magnetic field to the 2/5 power. Remember before, when we talked about axion-induced linear polarization, it's scaled like b squared. But when you're dominated by the Euler-Heisenberg term, that b squared changes to b to the 2/5. essentially because the Euler-Heisenberg term is entering into the denominator in some sense, and it has the magnetic field in it too. So I'm saying that because we're less sensitive to the magnetic field here than you would naively think. So whereas when I was talking about white dwarf linear polarization, we were super careful about the inclination angles, we're a little bit less careful here because it doesn't actually play that big of a role. And then I'm going to say let's discuss this later because I actually don't remember exactly what we did for the inclination angles. We had to make some choices, but I don't remember how we made those choices.
Thanks.
Yeah. So I think I'm essentially out of time. So I'm going to skip the last thing that I was going to talk about. I'll just tell you what it is, and then I'll kind of jump to the conclusions. So just to tell you what you can ask me about later, if you're interested to hear about it, is we recently looked at these same magnificent seven, not just for, kind of jump ahead to it, not just for X-rays, but also just we looked at the back reaction of those axions on the cooling of these neutron stars. So this is very much in the same spirit of Alessandro's talk yesterday, where he's talking about cooling of stars. Here we're looking at cooling of neutron stars, these same magnificent 7 neutron stars. So we have to go to slightly higher couplings in order for the axions to actually affect the cooling of those neutron stars, but then we can start to see the effects of their cooling. And so from this, we're able to set constraints on the axion coupling to nucleons. I'll kind of jump to the money plot, but I can go over this later if you're interested. So at the end of the day, we're able to constrain the mass of the KSVZ QCD axion to be less than 16 millieV, which is essentially the same as the constraints that we heard about yesterday. And this is the constraint in the context of the DFSC axion. So I'm not going to say any of the details here, but again, happy to chat with them offline. But to conclude, yeah, and if you attempt to make some, to put that constraint on this parameter space, it kind of looks like this. Of course, you have to make some model choices to go from the axion-nucleon coupling to the axion-photon coupling. But with kind of KSVZ-like model choices, you can think of the constraint as being roughly what's shown here. And the really annoying part of this whole game is that all of these constraints are essentially the same, which is just really weird. Like, why should magnetic white dwarf polarization and cooling of neutron stars and CAST give almost the same constraint? But everything seems to conspire to have roughly the same sensitivity, which is the very frustrating part of this business, because we want to be pushing down the lower couplings here. I think as we push down the lower couplings, there's really a good chance that we're actually going to detect something. And so what are we doing going into the future to push the lower couplings? So how do we get down here? That's really the big question. So I talked about magnetic white dwarf polarization. I said that can maybe get us to a few times 10 to the minus 13 inverse GeV going into the future, but that's probably where that's going to bottom out. So what else can we do? There are the spectral modulation approaches, which I haven't talked about because that's not work of mine, but that's what this NGC 1275 is coming from. And this is looking at X-rays coming from extragalactic clusters, from the centers of those clusters. As those X-rays propagate from there to us, they can undergo spectral distortions due to modulations into axions. That can make wiggles in the data. By looking for the absence of wiggles, you can set constraints. And in the future, that should be able to push down maybe close to 10 to the minus 13 inverse GeV, but you're going to become increasingly limited by systematics. These are already subject to systematics because you have to make assumptions about the magnetic fields, the number, density of electron profiles in these clusters. There are huge uncertainties there. So that's maybe not, it's an approach, but the robustness of that is going to have to be established at the same time as new instruments increase the statistics. So I don't know if that's kind of the unicorn we're looking for. So what is the unicorn? That's maybe, hopefully someone here, maybe this week we can find this unicorn, but I think there's some idea out there that's going to push us down to lower couplings, something which isn't going to conspire to give the same constraint to something else. And I think that's a really interesting question to be thinking about. Even if it costs a whole bunch of money, I think it's worth thinking big here and thinking about what even in principle are the ideas that can bring us down to 10 to the minus 14 inverse GeV, for example, because it's a really motivated region of parameter space to be going after. This is not the unicorn, but one idea which I've been brainstorming recently, which I'm just going to kind of sketch because I can discuss it more offline, which I think is interesting, which could get us down to a few times 10 to the minus 14 inverse GeV, is looking at axions being produced in pulsars and then detecting them with DM radio gut. So this is actually looking for kind of axions being emitted from pulsars at the rotation frequency, so like 100 hertz, and then looking for those axions actually with direct detection experiments, so repurposing experiments like DM radio gut to not look for the QCD axions, but to look for these low mass axion-like particles. We think in the future we might be able to get down to 10 to the minus 14 inverse GeV. This is work in progress with Ani Prabhu. Happy to chat about that more offline. So thanks. Happy to take more questions.
Any other question? No? Oh, Alessandro.
Concerning this magnetic dwarf polarization, which is the typical distance of these stars?
Good. So what's the typical distance? So first, it actually doesn't matter for the white dwarf polarization search, the distance, because we're not looking for the flux isn't being attenuated. We're just looking for the relative intensities when we compute linear polarization. Of course, the farther away, the less statistics at the end of the day, but we're not statistics limited here. So I don't actually have the distances off the top of my mind. So the magnetic white dwarf that we look at for X-ray was 30 parsec away. And that distance is very important because
20 parsec.
30 parsec. That distance is important because we're looking for something over nothing. And so the farther away the signal is, our flux goes down like 1 over r squared. But for linear polarization, since linear polarization is relative intensities, the distance actually doesn't play a role. But my impression is that all of these are within 100 parsec that we're looking at.
No, the reason why I'm asking is not for this flux attenuation, just a curiosity. So in principle, could there be some effect also of the galactic magnetic field?
Good. Yes. Yeah, that's a great question. Yeah. There is an effect from the galactic magnetic field, but it's subdominant. Yeah. Now I know what you're asking about distance. Yeah, it's subdominant for those magnetic white dwarfs. But let me just back up to, okay, so this star cluster limit, which is shown here, this is another kind of thing that a limit that we set a few years back.
That is important.
Yeah, and there we are looking at axions being produced in massive stars near the galactic center. And in that case, the galactic magnetic fields dominate the conversion probability. But yes, we've checked that for these X-ray probes, for example, they're closer and the magnetic fields are stronger, and there it's the star which is dominating. But there's, you know, an ensemble of other choice of other stars, and you should check it on kind of a case-by-case basis.
Because maybe 100 parsec could have some impact.
Yeah, right.
Because it's more or less the distance of Betelgeuse. So
that's right. That's right. Yeah, but for these magnetic white dwarfs, the B fields are really strong. But yeah, you might be able to use that to your advantage. You know, just brainstorming by thinking about some other source, which is going to be emitting unpolarized and looking for an induced linear polarization just from conversion of the galactic magnetic fields. That could be, you know, choose some really nice black body on the other side of the galaxy, which happens to be coming near the galactic center. Maybe you could use that to do some version of this too.
Thank you.
Yeah.
Any question on Zoom? No, so we had many. Oh, one more here.
So I would like to ask on the back on the first slides, and whenever you said about this cutoff, right, of the decay constant. So in principle, that can be lowered by lowering gravitational cutoff. So in principle, it can be lowered even at like the scale of like TV or something. If gravitational cutoff is too low because of species.
Sorry, so you're talking about the motivation. Okay, so you're saying that decay constant could be lowered in the context of these string models.
Oh yeah.
Oh yeah. I agree. Yeah, it could be lowered.
Of species, then gravitational cutoff can be lowered even at the TV scale.
Yeah, I'm just talking about kind of generic expectations,
Right.
but maybe my generic expectations differ from your generic expectations. At the end of the day, it's just motivating the parameter space that we're looking for. So so from my perspective, just taking everything to be generic, all the kind of everything at the string scale, I want to know near the Planck scale. I think it's an interesting question to ask, what do you kind of expect in that context? But I agree that things could be, you could have strongly warped extra dimensions, for example, and everything could kind of move down to a lower scale.
Right.
And so from a bottom-up perspective, we should just look for everything. But my point is just that even when you take everything to be generic, you still find this part of the parameter space to be populated in the context of explicit string theory constructions, where you naively wouldn't. And I think that that's pretty compelling.
Just a comment on
Yeah.
On your I mean, so as you said, it is important to go below. It's interesting to know that if you consider this neutron star cooling, so there is a window just below the cooling, so around below the 10 millielectron volt, where you I think you don't have any experiment which is sensitivity, because up to some millielectron volt you can have, for example, mad max if there is dark matter, so you can cover, but there is a gap where essentially it seems that there is nothing as far as I know.
Yeah, that's a great point. Actually, I was going to make that point, and then I just skip over it. But yeah, it's a really good point. So right. So just to kind of say that again for everybody, there's down here you expect the axion to be dark matter. Up here it could be dark matter, but it could also not be dark matter. So I think one, really powerful aspect of the probes that you discussed yesterday in these neutron star cooling probes is they don't actually require the axion to be dark matter. They're just looking for axions in the spectrum of nature at 10 millieV, and that's probably, it could be dark matter, but also just could exist in the spectrum of nature, and that's a more robust way to go about it. But then between, as you say, the top of mad max and where these stellar cooling constraints are coming in, there's a gap, and that's another gap that needs to be closed. I mean, we have essentially experiments that are going to cover this entire mass range, except for that gap. And that's an interesting gap that we should also be thinking about how to cover, and ideally without making too big of an assumption about the dark matter, because it might not be dark matter at those masses. Yeah, good point.